Bonjour à tous.
Good morning, everyone. Yes, we started talking about climate change a little. We have the lever of genetic variability. Someone told us about practical production methods. It can be discussed in the questions. The message I would like to tell you about is another lever. We can discuss how powerful it is, but first I need to tell you what it is: plasticity. So, overall context, I assume that you know this kind of curves. If not, well, good for me, I put one on. The evolution of temperatures given the various climate scenarios. Some people will tell you that policies can change in terms of temperatures. It can be modeled, and the consequences can be studied in terms of hydric impacts. So we have a rather refined notion on what's going to happen with climate change. So the question we ask ourselves is how are plants going to react to that? So the biological impact is much stronger because plants have levers that we don't understand yet. What are these levers? First of all, migration. When I say that, I'm talking about natural populations and cultivated places, because if a culture becomes more adapted to another territory, it will happen. But also adaptation and selection for agronomic species. It's based on genetic variability, which is why we need genetic resources that remain varied. And there's the lever of acclimatization. It's the capacity of a plant to adjust its metabolism to new conditions. And this is what we call phenotypic plasticity. In this plasticity, of course, it's also depending on the genetics, partly. So this is the small arrow you see at the bottom. It also depends on a level of genetic variability. Let's take some examples. What is phenotypic plasticity? It's the variation of phenotypic characteristics, so characteristics induced by the environment. What characteristic do you want to look at? For instance, the color of a leaf. We have a green leaf, and depending on the environment, in number one environment, it will be green, or it can turn green in another environment. That's plasticity. Or you can have a green leaf for one genotype, one individual, a pink one for another individual, and no matter the environment, these individuals will keep their different colors, and that's what we call genetic variability. And most often is I have green leaves that can change colors in a different environment, and this change of color will change more and more based on the genotype, and then we have a genetic variability of the phenotypic plasticity. That was the example for the leaf color. This plasticity is not always a good thing. What we want is the adaptative plasticity. It's the one that can improve the capacity of a plant to survive in a new environment. This is the theory. Of course, what's important is to identify the parameters that are the most relevant to us. When talking about drought, for example, that's what Berlin told us. The tolerance to, or the resistance to drought, more globally, is based on a lot of parameters that we've summed up here. What are the levers that a plant can use? There are two strategies: either to avoid drought. How do you avoid drought? You reduce the water loss, so you close your stomata. It can reduce the permeability of or the waterproofness of the cuticles, and it's more or less developed, or it can modulate its leaf surface, either brutally. If a plant loses its leaves very quickly, it can be part of its strategy. Some plants can recover from it, some can't. Another strategy is to increase the water intake. They dig deeper with their roots, or they increase their root density at the same depth, but more dense. And some other strategies enable them to tolerate. I make a difference between tolerating and resisting. Tolerating means even if there are more and more restrictions, I can still survive. It's not the same as avoidance. So the plant will lose water, but resist to it. It will reduce its sensitivity to dehydration. It will accumulate a lot of components that help it in its osmoregulation. It will produce antioxidants. That's what happens at the cellular level. It can also mobilize its water reserves. The plant has water reserves, and it can use them up to avoid the impacts of the drought. There's also the resistance to xylem embolism, because that would have a bad consequence on the plant, and I'm going to develop that aspect when I talk about resistance to embolism. That's what we mean by these mechanisms. So whether it is plasticity or genetic variability, you need to understand those processes. It will lead to choices that can depend on the environmental context, for instance, but other things. Imagine you have a very thin soil, roots won't go deeper, so you can forget this parameter. If you have deeper soils, you know that maybe I can develop varieties that have a deeper rooting system. So it enables you to choose the parameters you want to focus on. In the RECITAL program, we had made choices that are also related to our skills. We looked at the closing up of stomates, because it's the #1 system to avoid loss of water. And also the osmoregulation and the resistance to xylem embolism. So a few reminders on how the hydric system and the hydraulic system works in a plant. To absorb water in its roots, the water does that because it loses water evaporation on the top part, the leaves. There is a continuum, a hydraulic continuum. When water is leaving through the leaves, the roots can absorb water. It's very efficient because it costs zero energy. Basically, the light of the sunlight brings it. The natural evaporation through the atmosphere pulls the water in the root. But it's very sensitive and dangerous because there is a risk of embolism. Why? Because when there's evaporation through the leaves, it's a tension that's being created. Tension is the opposite of pressure. So it's measured in bars, it's a pressure, or megapascals, which is even more important in terms of humidity. So these tensions are negative, because it's the opposite of pressure. In a soil that's saturated in water, the tension, is zero. Same with 100% humidity atmosphere. The potential is zero. And the more you go below zero in negative characteristics, spring in our temperate regions, for instance, minus 70 MPAs. So that gives you the tension in the atmosphere to attract the water into the plants. It's between 0 and -1 in the soil. And in the plant, it's between -1 and -10. But the risk is as we say, the more you pull on the rope, the more risk you have to have it breaking. So embolism is a bubble of water that would enter a vessel. Here, a picture shows a bubble of water in the root, and this is gas embolism. Then you break the water circulation in the water. That's what we call cavitation. When there's been cavitation in the plant then cannot fuel its higher parts in water.
So you've got loss of conductance, you've got gaseous embolism. And what do you have then? Well, you have cavities which kill. It's quite like fumiteur. We say, no, well, cavité is like from the Latin. It's a caveat. These holes can, this can kill. Smoking can kill. So when you look at the hydraulic function, you have to see that it's a system that's always under tension that allows this water in, but it's a process which is extremely sensitive, so you almost have to be beware. So what have we done in this recital program? Well, we wanted to change, modulate, use plasticity. So you can see we've got plants here. We've got cuttings of feet of lavender, looking at the capacity they have in the field. And by that we mean that a soil which is very water heavy. And then beside that, you have a different system, a system of weighted pots. And we're able to regulate water intake. We can measure, we can control the amount of water in the soil. It's usually between 25 and 30%. Why? Well, we realized that this was really what was able to produce, allow the plant to grow at its minimum level. It's the minimum quantity of water necessary for the plant to actually grow. So that was the most important water constraint that a plant could have. You know, out with that, the plant was not going to grow. So there were a certain amount of measures put in place. You can see that there is development on both sides. For those which are irrigated, you can see the surface is greater. We also did this we did it on lavender and the Mayette variety, and lavender and grosso. So we've done this to compare the different species. Then we moved on, monitoring growth, thanks to probes or sensors, which allowed us to monitor diameter and growth. And this is kind of raw results in front of you. When they're well irrigated, you can see there's no problem in terms of growth. What you have to look at the values, of course, which you probably can't see. You can see the growth over a period of several days. They grew about 2 millimeters. But those that were suffering from water stress, with the blue drop, you can see it's a different growth pattern. Growth is lesser. And you can see that over the course of the day, it's too dry. The roots are constrained, they retract. We also looked at the state of water, to make sure we had different water states, looking at the water potential, and this allows us to monitor the water state. The more it's negative, the more your plant is needing water. On irrigated systems, you can go down to 0.7 for lavender or fine lavender, and you can see the hydric strength is no longer negative. Even though the foliary surface is restricted, they are still under water stress. What does that really mean? Well, we looked at stomatic conductance, you know, the ability to breathe, and we can see those that are well irrigated. The results are fairly high for this type of plant. Those who are under water stress, well, they have a stomatic conductance which is naturally reduced. Now you can see clearly that for those who which are cultivated in a nice water system where they have enough water, they've got less gas. So how would they behave in the face of a drought? Well, we open the valves, if you like, to see what's good. What do we do? What do we do to create drought conditions? We just stop watering the plant, let the plant manage itself. So the first thing we measure is the hydric potential. When you've got water, you look at the hydric potential of the plant, the hydric stress on the plant, and you can see the grey sticks are the ones which are not getting the plants which are not getting any water, and the other ones are ones which are still receiving water. When you stop watering, those which are in hydric stress which are obviously, you can see them contract, the ones in hydric stress. But then we water them all. What do we do? Well, we soak them both then to measure their response after drought. And this is the same. You can see the results for Lavandin and for Fine Lavender, where you see that those plants are in a favorable hydric position very quickly are in a very constrained position because the water, they're engorged. And this isn't the same then if you look at the right-hand side for the ones which have already been under some kind of water stress. They find themselves in a water stress which is actually less restrictive than the others. It's a form of plasticity. The plant, the growing conditions has actually rendered them less reactive to drought than those which have been cultivated with the right amount of water. So, in a drought, those who have been cultivated under stress, water stress, actually retain their capacity to grow. So this all comes down to our way of managing water and their way of managing water. Same experiment then. We stop watering and see what happens. Then you re-water. What happens? We put all of the water in, all the water they need, and you're all at the same starting point. And then we look at the results. How do they behave once we stop watering them then? We're actually quite surprised to see those that were in a favorable water position have stomatic conductance, which is higher on Lavandin and Fine, but very quickly, this goes down with drought. So they're going to lower the stoma, in order to conserve water. When you water the ones on the left, they have a better resistance. But when you stop watering them, the ones on the right, they still have a better resistance to drought than the ones on the left because they've been less used to having water. They continue to have gas exchanges which are superior to those which have been used to living with a great deal of water. So that's interesting in terms of plasticity. They develop better. They have a better gaseous exchange during drought because they've been used to this. You've been used to constricted water conditions. So you have reduced conductive stomatic conductors, a better resistance to drought for the plants on the right because they're used to it. That's the bottom line. Now, the other parameter that we considered, and we've been using it to measure for some time, is the resistance, the vulnerability of the XLM to embolism. If there's embolism, your plant is going to die. So this is all about survival. We are able to measure it, especially with a modified centrifugal system. The centrifugal force is a force which actually resembles drought because it makes the branch turn. We simulate drought by making the branches turn in the centrifuge. So if you measure the speed of that, we can look at the force, the pressure that you put on the plant. So we have a measure where we can look at the point of vulnerability and for embolism, depending on the tension or the pressure that is used. So this is what we've done for Lavandin. When you look at a very precise parameter, we look at the pressure, which produces 50% of pressure. This pressure is roughly minus 6 megapascals, roughly. This was a Lavandin grass which was plucked from the middle of a field. Now, we did this for cultivated plants that have been cultivated with a great deal of water, in a very favorable water condition, obviously. You can see the curves here for lavender and for Lavandin. Now, you can see you're talking about minus 286, minus 3, and this was what we can see in poplar trees or plants which are very sensitive to drought, for example, gooseberries. We made these plants very vulnerable to cavitation by developing them under a favorable water regime. Now, it's as if the plasticity was adapting itself, and this is allowing the plant to develop better. Your plasticity actually renders your plants even more sensitive to water stress. So we had to ask some questions at that point. These are the results. I talked about the results that we took from the middle of a field. It was minus 6. We'd never seen this. This is really we witness a plasticity which is very high. We had some doubts, so we had to check this. We checked all our measures, and that was a centrifugal method. We're going to use an embolimeter. We're going to cup the branches, we're going to dry them and see how that changes. And we actually got the same result. We sent plants to the synchrotron, which is a particle accelerator. It's another technique in order to check that this wasn't just some random sample. No, that this was actually a real and true result. And on whole plants, we found the same kind of curve. So we have confirmed that the favorable water conditions renders our plants more sensitive in terms of drought, more sensitive to embolism under those 3 testing conditions. And that's one of the factors of plasticity. So what we concluded from all of this was the following. With these, there is plasticity with hydraulic traits, which is fairly important in lavender, or with this be stomatic conductance, or the pressure. And this means that we're going to have to consider the genome, and that's what we do anyway when we look at selection. We go to selection plants which are going to resist better, but we also have to ensure the following, that there is this plasticity. When you see there is a genetic variety for phenotypic plasticity, these are 2 parameters, 2 levers that must be considered when you try to improve drought resistance of one species or one variety, or even certain varieties. That's just a various reminder of the various participants who have been involved in the project, because with this within the RECITAL project, it was almost ancillary to the other projects which were ongoing. So thank you very much, and I would love any questions. I have a question. You talked about variability. What are we talking about? What is inherited in the plasticity? Because if we define a production method for any kind of primary plant, is this going to have an impact on the shrubs? Or is it going to adopt the same itinerary, the same cultivation itinerary as the mother plant? Well, you have to talk about genetics here. There are 2 questions in one. I'll try and give you the best answer possible. The phenotypical plasticity is dependent on genetics. You can see plasticity which is more or less present depending on the genes. If I make sure that my vegetable content is used to developing with plasticity, then it's possible that under different conditions that this plasticity is wiped out or that it is maintained. It really depends on the parameters, the traits. I'll give you an example. If this stomatic conductance, as I said, well, this conductance, you have to see on what it depends. It depends on the number of stoma on your leaves. And this means as soon as it's well anchored into the plant, it's not going to move as long as it's on those files. But however, as soon as there's new leaves, well, it's possible it can be adapted. So it's something that's evolving all the time. There are parameters where it's going to last longer, embolism resistance, for example, and other parameters where it's dependent. Laurence Moulon, I'm a toxicologist. Have you made any kind of correlation between this plant adaptation and the secondary metabolite composition, for example, for lavender, if you look at essential oil, for the quality of the essential oil? Not yet, indeed. I'm saying not yet, because that's going to be part of a secondary program that we're doing. I think it's very interesting. I think it's extremely interesting. And I think the result might be even more interesting. Well, we know from the literature that there is an impact on the VOCs. Depending on the drought, in quantitative measures, we know there are measures, but also there are differences also in a qualitative section. We realize that what we really have to do is identify the factors of water stress, because depending on them, you're going to have responses which are going to be very different. It's fairly conflictual, actually, and actually quite contradictory in the literature, because water stress is not necessarily well managed. Well, for example, if you talk about distillation and regulation, we're going to try to limit these volatile organic compounds and try and stick to components to other oxygen-producing components. Nicolas Jacteur, I'm a producer. With some plants, we say that you haven't to water them at the beginning in order to let the root system develop better and for the plant to really set in, the growing process to begin. You didn't really talk that much about roots. I think that one of the conditions which would help encourage plasticity in the future is root colonization. For us, as producers, it is the ground at work, the soil at work, and we have to have irrigation in place to stimulate the root at the beginning so that the root can really, we can see correct root uptake. So it's very difficult to modulate the amount of use of water in the soil at that stage. Well, yeah, absolutely. That's what I've been saying. We have to be very careful about how we water at the beginning. I didn't really talk about roots because we've studied this, but as I said at the beginning, there are many parameters to consider, and roots are part of this. Now, what do I mean by vibrating? It's not just on the roots, it's also on the characteristics of the leaves. This can be, for example, on the vine. And what happens there? They're going to be more resistant to drought because the stoma conditions are going to be weaker, and they're maintained in drought conditions. So that's basically what I said.